So today we're going to talk about something called kinetic molecular theory, and we're going to talk chapter 10 and 11 kind of as a combination chapter. So chapter 10 is very short. We'll get through it pretty much today. Okay, it has to do with something called kinetic molecular theory. Chapter 11 has to do with the gas laws, and we're going to start studying gases and the way they react, the way some properties of gases. But chapter 10 and 11 are going to go together. So let's talk about kinetic molecular theory. What does the word kinetic mean? Moving, motion. Good. That root kina means motion. So motion of molecules. Okay, that's pretty much it. Okay, molecular motion. That's what we're talking about. The theory of molecular motion. Why molecules move the way they do. What gives them kind of the incentive or the means to move the way they do. Things like that. Okay. So kinetic molecular theory. This theory is going to have quite a few ideas. We're going to look at a couple different versions of the theory, kind of a new and an old. But basically, this theory is based on all the fact or the idea that all particles are in constant motion. Okay? All particles are in constant motion. So which particles are probably going to move more? Gas particles or solid particles? Gas particles are probably going to move more. Okay? What do solid particles kind of do? They vibrate, they move back and forth, but very, very...
They move faster.
They might move faster, but they move... in terms of space they cover, yeah, they're going to move less, okay? But they're going to be moving less, okay? So all particles are in a state of constant motion. So what kinetic molecular theory does is we're going to look at the theory's connection between gases, liquids, and solids. So we're going to be able to apply this kinetic molecular theory to all three phases of matter, okay, or the main three states or phases of matter. Okay. All right, so we're going to look at kinetic molecular theory of gases first. Kinetic molecular theory of gases. We're going to deal with something. We're going to deal with a gas that's considered an ideal gas. Okay, what's it mean if something is ideal?
It's a better situation.
It's a good situation, right? Ideal means pretty perfect, okay? So an ideal gas is hypothetical, okay? In the real world, gases don't necessarily behave this way, but we're going to look at ideal gases, right? In our theoretical chemical studies, we're going to be able to look at things that work exactly how we want them to work. Okay, so ideal gases are hypothetical, but they perfectly fit all the assumptions of kinetic molecular theory. So we're going to go through some assumptions that have to be true in order for it to be considered an ideal gas. Okay. So there's 5 of them. 5 assumptions that have to be true in order for something to behave like an ideal gas. Okay. These assumptions are going to seem kind of common sense to us, okay? But these things have to be true in order for it to be considered. And you don't have to write them out word for word, okay? Paraphrase them, shorten them into your own words so you can save some time, okay? So the first assumption that has to be true is that it has to be a large number of particles that are far apart. Okay, so large number, small particles, they're far apart. Do you have any idea what it means when it says relative to their size? They're far apart relative to their size.
Compared to their size. I mean, if they're tiny, then they can only be like that far apart when it's like big.
Yeah, perfect. Okay, good. Okay, so relative to their size means they might be a millionth of a millimeter apart, right? They might be a millionth of a millimeter apart, but that might be, the distance of 40,000 particles, right? So we're talking about they're relative to the size. So if we shrink down and look at things on the molecular level, those two particles would be really far apart. Even though to us a tenth or a millionth of a millimeter is obviously not a very far distance. Okay, so we have to think about that thing relative to their size. Okay, These two things we know. You don't have to write them down, but it's just kind of reminders. Gas particles are farther away from each other as comparison to solids or liquids. Okay, hopefully that's self-explanatory. Hopefully that's something that we know most of the time. Okay, gases and most of the volume of gases is made up of just blank space. Right? If we have gas particles that are far apart from each other, what has to be between them? Yeah, nothing, right? There can't be anything in between them. If this is an air particle and this is an air particle, right, it's not air that fills it, it's blank space, right? It's nothing. Okay, so we have to kind of think about that. But that's what we're talking about for the first assumption. So large number of particles that are small, that are far apart. Okay. Number 2, collisions between gas particles and between particles in the container are what we consider elastic collisions. There might be one person in this room that knows what that means. Kiana's in physics, that's why I'm saying that. Yeah, they bounce apart. Some of you also might know what that means. Okay, but we studied it in physics, so I put Kiana on the spot. Okay, elastic collisions means that they are going to collide and then they are going to bounce apart. Okay, so collisions between two gas particles or between the gas particle and a wall mean they're elastic collisions, so they are going to hit and bounce off. Okay, the opposite of that would be what we call an inelastic collision, in which they would hit and then stick together. Okay, that's not what happens in gas particles. They hit and then bounce back apart. Okay, where do we see that type of collision in real life? What's a good example for an elastic collision in real life where two things would hit and then bounce off?
Two people running
Tennis ball.
exercise balls and they're like,
Okay,
Tennis ball.
it's a random example, but okay, yeah. When we talk about a perfectly elastic collision, that means we have no loss in kinetic energy. So if we're talking about kinetic energy, that has to be energy of what? Energy of motion. Good. So if we have a perfectly elastic collision, that means one particle would hit another and perfectly transfer all of that energy to the other particle. Okay? No loss in energy. Assumption number 3. We are in continuous, rapid, random motion. So these little gas particles are continuous, rapid, and random motion. We're talking about random and rapid motion. Do you visualize these gas particles moving in spirals or in circles? Or how do you visualize these gas particles moving? However they want. Okay, do you think they're moving in curved lines or straight lines? Straight lines. Okay, they move in straight line paths. So whatever energy they have is going to put them in straight line, right? Newton's first law tells us an object will stay in motion until something else acts upon it. So that gas particle is going to move as fast as it has, as much energy as it has, as fast as it can, toward that direction until something stops it. Could be another particle that knocks it off course. It could be the container of the wall. Whatever it is, it's going to move in straight line motions until something stops it. Then it's going to bounce back and move the other way. Okay, so we've got to think about straight line motion. Fourth assumption, there are no forces of attraction between gas particles. Okay, so when two gas particles get close together, they're not going to attract each other. Okay, remember we're talking ideal gas here. Okay, so in real world applications, we're going to see a force of attraction, but when we think about ideal gas, we don't want anything slowing us down, so we think no forces of attraction between these two particles. Okay, and that's because they're like pool balls or like billiard balls. Okay, they bounce off each other. They don't stick when they collide. They just bounce right off. Okay, that's an elastic collision. Okay, last assumption that goes with an ideal gas. And it has to deal with the kinetic energy, so the energy of objects in motion, and the temperature, and the relationship between those two things. Okay, so kinetic energy gives us a way to gauge the temperature of an ideal gas. Okay, the temperature is dependent upon the kinetic energy. Yeah, it increases, right? If we see an increase in kinetic energy, which means those particles are moving faster, okay, they have a greater amount of energy. When we see an increase of energy, when we input energy into something, what happens to the temperature? It rises, okay? And if the kinetic energy decreases, if you slow down, right? If these things aren't moving as fast, if we see less collisions and less transfer of kinetic energy, what do we expect the temperature to do? It decreases. Okay, so you can see these things in your real life, right? When you are moving faster, okay, when you start to increase your energy, you'll see an increase in your temperature. Okay, when we see a decrease in energy, we see a decrease in temperature. Those things connect to us real world. Okay, so now let's talk about real gases just a little bit. We are going to deal almost exclusively in this chapter with ideal gases. They follow those rules, but I'm going to show you kind of what are the changes that what happens when we talk about real gases. Okay, so real life. Particles in real gases do have a volume. It's not just necessarily the volume of the container that we're talking about. Real gas particles do have a volume, okay, that will affect the overall volume of the system. Okay. If they have attractive forces between each other, are they strong enough to pull those gas particles together? Yeah, probably not. They're pretty far apart anyway, and they're gases, so they don't stick together, right? They have attractive forces, but they're so small they get broken really quickly, okay? So in real world and in real gases, gases do behave ideally, right? They follow those 5 assumptions most of the time, except for these 3 times, okay, these 3 situations. If we have really, really low pressure, if we have really high temperatures, or if we have nonpolar molecules. Okay, we have what we need here? All right. So now let's move on to kinetic molecular theory of liquids. Moving into liquids and solids, they're really pretty common sense. Gases is where we see the most relationship between kinetic molecular theory. But we'll go through, review these really quickly. Most of these you'll kind of know already. Okay, liquids have definite shape but no definite volume. This is something that you've heard probably 30 times in your science career, right?
You said definite shape.
Sorry, you might not have heard that. Okay, they have a definite volume but no definite shape, my bad. Okay, hopefully you didn't write it down wrong. Okay, they do have a definite volume but not a definite shape. Okay, we've heard that before. Particles are closer together than solids. They have stronger intermolecular forces than gases. Okay. Okay, intermolecular forces, are those forces within a molecule or between multiple molecules? Between multiple molecules. Okay, so intermolecular forces are what is holding a liquid molecule to another liquid molecule. Okay, that's why they have much stronger intermolecular forces than gases do. Okay. Good, definite shape and a definite volume. They have more molecules that are packed closely together. They have the stronger intermolecular forces, but those particles are still in motion. Okay, we talked about they have more of a vibration type movement. Okay, so still in motion, but more of a vibration than a constant, random, rapid motion. Right? They're not so random. Oops.
So we just went over all chapter 10.
That was it. That was chapter 10. Kinetic molecular theory.
So how long was...
Colin, be ready.
Yeah.
What?
Gas laws, there's about 5 gas laws. We're just going to go through conversions to begin the gas laws today, and then we'll start on with the actual equations next class. But we're going to talk about something called STP. STP. STP stands for standard temperature and pressure. Okay, STP stands for standard temperature and pressure. Okay, you need to know what STP is. You need to know what it stands for, and I'm also going to give you a temperature and a pressure that make up STP. Okay, so if I tell you this experiment was conducted at STP, that means it was at a certain temperature and a certain pressure. Okay, so it is a set of conditions. That's what STP means.
So what
Okay.
you're saying, we need to know that for the test.
You need to know that for the test, yes. Okay. The units for STP, temperature has to be measured in Kelvin. Temperature has to be measured in Kelvin. Do you guys know any units for pressure? No, that's a speed unit. All right, yeah, okay. Okay, so let's talk about temperature a little bit more. Conversions from Celsius to Kelvin, you add 273 to any Celsius measure to get to Kelvin. Okay, so Celsius to Kelvin is very easy. Okay, Celsius to Kelvin is very, very easy. Add 273. To get from Celsius to Fahrenheit or Fahrenheit to Celsius, that's the conversion that you would go through. So you might need to have that one down. Okay, have you seen the Celsius to Kelvin conversion before? 273? Yes. Okay, good. Fahrenheit to Celsius is less common and more complex, but we have to do it because, you know, in America we got to measure in Fahrenheit, apparently.
We have to be different.
Okay, I won't give you Fahrenheit values very often, if ever. Okay, but you need to have that down probably. Okay. Do we know what's the freezing temperature in Celsius of water? Water. Okay, and boiling point of water in Celsius? 100. Very simple, right? Okay. So STP units for pressure are called atmospheres. ATM is the abbreviation, but it's called atmospheres. Okay, and I know you guys will just say it's this many ATMs, and that will drive me nuts, but it's called atmospheres. Okay, ATM is just the abbreviation for it. All right, so when we talk about pressure, you guys I think all know what the concept of pressure means. Okay, but the actual equation for pressure is a force divided by a certain area. Okay, so if I apply a larger force over a small amount of area, that's going to give me a pretty big pressure, right? But if I increase the area that I'm applying that force, what would happen to my pressure? It would decrease. Okay, so do we see the relationship there? Okay, a larger force over a small area is going to give you a big pressure. As you increase that volume or increase that area, we're going to see a decrease in pressure. Okay, and we're going to be able to connect volume and pressure and temperature in this chapter in terms of gases. Okay, but pressure conversion, since we want all of our units to always be Kelvin and atmospheres, I'm going to give you the conversions between several other different kinds of pressure. Okay, we measure pressure in about 4 different types of units. Don't know why, but we do. Okay, so I'm going to give you the conversions to do that because you're going to always want your pressure in atmospheres. Okay, ATM.
Pressure stands for, or ATM stands for.
ATM is atmospheres. That's a unit for pressure. Okay, so here are the conversions for pressure. So you're going to need to know these conversions. 1 ATM equals kPa, which is kilopascal. This is millimeters of mercury. This is called torr, and this is psi. A kilopascal is just another unit for pressure, and it's a pretty common one, kilopascals. If it gave it to you in just pascals, we would convert from kilopascals to pascals, and it would say 1 atmosphere equals 101,325 pascals. Okay? You can. It doesn't really matter. If you can convert from regular to kilo, then you don't need to write it down, but you can if you want. Okay, all of these conversions you need to have down because that's what your homework is going to be today, is working on these pressure conversions.
Do we need to know like what the abbreviations stand for, or like the MHD or the...
Yeah, this is millimeters of mercury. You need to be able to speak them, know what they like. You know, you're going to be able to need to say them. Kilopascals, millimeters of mercury, torr, and psi. Torr is just another unit. I don't really even know what torr is used to measure. I really don't know that. I could look that up. No, it's not minus. It's equal. It's just torr, T-O-R-R. It's just another unit. I'll have to look up what that's usually measured for because I don't know what that's for. PSI stands for pounds per square inch. Pounds of pressure, pounds of force over this many square inches. Okay. Millimeters of mercury, do we see where that comes from?
Yeah.
Listen, millimeters of mercury, 0 degrees Celsius and 1 atmosphere. Oops, sorry. Okay, these are the conditions. These mean the same thing. 0 degrees Celsius and 273 Kelvin, that's the same temperature. This is the same amount of pressure, okay? Realistically, you're going to want it in Kelvin and atmospheres all the time. So your STP units are really 273 Kelvin and 1 atmosphere. Okay, so if I start a problem with 4 liters of gas is at STP, you have to know what the temperature and what the pressure is there. Okay, so those conditions, that set of conditions, you'll have to know. 1 atmosphere, 0 degrees Celsius, or 273 Kelvin. Okay, luckily they're easy values to remember.